that DC won't go into the capacitor. It will go to the emitter, supplying the electric current. Signals. If you signal at the input of that transistor, there will be no signal at the emitter. Why? In a small signal model, your emitter is grounded. Here, emitter is short circuited. So this is genuinely a CE amplifier. Do you remember that we had an RC in the collectors? So the I that you are biasing here, IC, is going to give you the GM. IC over VT. And the gain of this amplifier, AV, would be equal to minus GM times RC. That's a VCC, some values. All right? That's the gain. How can I increase this gain? Number one, biasing GM. You have to get a large GM. For getting a large GM, I need to have a large collector current. But collector currents are in the manufacturing are limited because the higher is the collector current, the more we are going to drain from our main battery. That's undesirable. So we would like to keep ICs to low. 0.5 milli, 1 milli, maybe 1.5 milli, nothing more than that. Second alternative, how can I increase AV, which is the output voltage here, divided by, say, VI, the input voltage. So this is VO over VI. Next alternative is go get a large RC, right? Large RC, that's logical, isn't that right? Because it's the product of the two. You get a larger voltage gain, certainly you will. But what's the problem with how large I can go on RC? If I increase RC to 100 kilo ohm, do you think it will work? Why it won't work? This is 15 volt, and that's say 1 milliamp, say. Okay. If I make this 100K, in order to get a pretty large voltage gain, why it won't work?
VC needs to be, or VCE needs to be higher than VE.
That's it, because it will be saturated. You see, if I send in this 1 milliamp through the 100K, it will drop 100 volt on that resistor. It doesn't have room to go to 100 volt because it starts from 15. If it drops, it will stop. Collector voltage will stop where this emitter is biased, maybe 1 or 2 volt. Okay, so the transistor will go into saturation. I can't increase the value of the RC just arbitrarily. You've got to be proportional so that transistor doesn't go into saturation. Now, think of this one. $100K, $1 milliamp, again 15 volt, same stuff, 1 milliamp, okay, and then same idea bypassed, CE, apply the VI, get the VO. So this is our RC. And that box is between these two terminals. Is a current source, actually a current source with internal dynamic dynamic resistance of 100 kilo. Then what will be our voltage gain, and what will be that saturation situation we were talking about? Okay, let's see. Here, this is 1 milliamp. All of the 1 milliamp is not going to go through the RC because this source is canceling it. See, take this over there. The 1 milli, this supplies 1 milli, but what is left over there is just the RC. So a collector load like that, it's called a current source active load. It's called active collector because it's going to be built by another transistor, just the same way that this one was built by another transistor. Except the direction of the current they are sending, it will be in the opposite direction. This will send from up down, this one will send away from the emitter. Collector current coming this way, emitter current exiting that way. So this current will cancel that current, and what you will get in terms of AC equivalent circuit, if you're going to draw that equivalent circuit, this will be your final output stage. First, this point will be a short circuit. Then you will have your GM times VBE. This is the R pi, and that's the VBE. Okay. Now try to model, that's the base. This is the collector. Okay, that's the base. Of course, that's collector, emitter. Now try to model that AC equivalent circuit, the small signal equivalent circuit. So what was the law, if you recall? We put the constants to 0. Remember, we put the constants like constant voltage source. This guy goes to 0. Okay, we will take it to 0. What is that? A constant current source, isn't that right? What do you do with the constant currents in the circuit? Don't you put them to open circuit the same way that you did with the constant voltage source to short circuit? So if you put this to open circuit, you're going to see, this is I won't even draw that, I'll just draw the RC equal to 100K. Now, I will try to determine the voltage gain. VBE, VO over VBE, which we can call this VI. VB or VI is the same thing, which is same as VO output over input, is equal to minus GM multiplied by the RC. So, if I had an IC of 1 milliamp here, let's say, if IC is 1 milliamp, then GM is going to be 1 milliamp over 25 millivolt equal to 0.04. GM would be equal to that. With 100K, it will go into saturation. I have to think of something. Maybe not more than 5 volt on the RC from the 15 to have a VCE point, a quiescent point. That means my RC is limited to maybe 5K in here, 7K, because it will drop 7 volt from here. So RC of 5 or 6 or 7K multiplied by that versus the 0.04 multiplying 100,000. This will be a shift, and that one also shift, 40,000. Minus 40,000. A voltage gain of 40,000. Why? Because by putting an RC of 100 kilo ohm in here, we have in parallel with the current source, that's a current source. Remember what I've boxed in here is a current source. It provides a constant current, but does have an internal resistance. You see? In other words, it's not ideal constant current source. If it was ideal, what would be the case? Oh, 1 milliamp going in here, constant, and 1 milliamp going out of here, constant. If it was an ideal one, my RC would be infinity. In that case, it would be GM multiplied by infinity. I could get an infinite gain out of it, which is not practical. But here, it's all pending to the dynamic resistance of that current source. How much gain I can get. Look, out of one stage, just one stage, I managed to create a gain of 40,000. As opposed, it would be typical here, I say typical. RC, typical, I say midway, like 7 volt, on that 7K. 7K at most. So my gain would be, AV would be 7,000 multiplied by 0.04, and that would be about, move 2 of them, 280. Remember in the CEs we used to get gains of 110, 120, 150, 180, that's typical. This is atypical. But here, 40,000 out of one stage is not typical. That something is done here. So this is done by a current source. So we are chasing now current sources that have a large dynamic resistance. It's possible to create them. And mirror image current sources especially. There will be a set transistor here which will not only supply the emitter current of a specific type of a transistor combination known as differential amplifier. This is not a differential. It's just the old one, old common emitter amplifier. We will use a set of transistors that will supply a constant current for the emitter, and then a mirror image current source that will supply from the top to the bottom another constant current which will balance the current over here. The two will balance each other. In the end, they will leave an equivalent circuit consisting of a pretty large RC. This RC is not added, it's not physically added. It's the RO of a transistor, the output impedance of a transistor, this one. Which in a minute we will see how they come along. Why it is RO of another transistor. Of course, I will show you the NPN version of that source, which is this source actually. This is implemented by NPNs. Implemented by NPNs. This one is mirrored by PNP transistors. Mirrored by PNP transistors. That's why, you know, when you look at a professional differential amplifier, say 741, you go crazy because there are so many transistors there, you wonder what they're doing. PNPs mixed with NPNs. Oh, this is what they're doing. They are creating current sources. Most of them are current sources. We don't need too many amplification. amplification is only maybe 2 stages, just 2 stages of amplification will give you a gain of at least 100,000. At least 100,000. Here, if one of them gives you this 40,000, how much do you need to make it to 100,000? You need another gain of 2, maybe 2.5. So you can easily build out of 2 amplifying stages, you can build gains of upwards of 100,000. Can go to 1 million, a gain of 1 million. Just two amplifiers, 2 stages. But these stages are not going to be that CE amplifier type with a resistor as a current source. Those stages will be smart current sources, smart circuits to bias them, and then smart collector resistors here. This collector resistor here, it can be a PNP amplifier like that. Actually, here with another one. Which is feeding from another reference source. This will be another reference source. It is known as the mirror image current generator. 2A minus VCC, usually. We need 2 supplies plus VCC. So there will be a reference current source which will set 1 milliamp in one. The other transistor will mimic, exactly produce the same current in here. 1 milliamp. Known as mirror current generator. The mirror current generator will set the reference for the top one, this top one, and then the next transistor will mirror that current back into here. So eventually, we will obtain a current that is going from the top downwards. Exactly what I said in here. So that will be the philosophy of designing active collector load resistors. It's called active collector load resistors, and current generators. In a minute we will get into that over this handout. Okay? It's a very nice thing, you know, very ingenious, very, very ingenious. How we can do that. So you got the idea why this fails. Just sticking a resistor here. For small amplifiers, low gain, you can do that, no problem, you know. 2, 3, 4, 5, 6K, it's fine. It will give you a gain of about 100 to 200, that's okay for small signal amplifiers. It's perfectly all right. We don't need all those balancers, just a resistor here will do, RE, you know, the one that we used it before. That would be adequate. But when it comes to something that you want to get away with a gain of 200,000, 100,000, or even more, 500,000, just 2 cascaded stages, that won't work. This will not work with 7K. You need to have active collectors. So basically this part becomes that box we were talking about, this part of it. Feeding that point, receiving from the top power supply. Okay, so here is the simplified version, and we're going to look into it. You don't take a picture of this one, take it, you know, that's not in the notes, because it just tells you about the philosophy of what we're doing there. The trend, the practice. Okay, so here, a note on current sources. There are different types of current sources. These are the popular ones, especially the second one is pretty popular. There is a modification of second one, which is more effective. It's kind of improvement. But we won't go into stages of improving these current sources, how to get closer and closer to the ideal one. That will be, you know, like too much. So here it goes. Mirror generator, which is essentially this one. How does it work? Mirror current generator, number one, simple current source, known as mirror current generator, consists of two identical transistors. These transistors are fabricated on an IC, integrated chip, absolutely next to each other. So in the masking process, it's just a micrometer apart from each other, basically. Therefore, both are going to have, if they use the same mask, both are going to have exactly the same concentration of charge carriers, same mobility because of their close proximity. It's not discrete, it's not apart from each other. It's the same location. And also same temperature. That's most important because they are within micrometer of each other. If one has a VT of 25 millivolt, the other one also has the same. If temperature goes up, it goes to 26 millivolt, the other one will be also 26 millivolt. They follow, they track each other. So here is the circuit. We use usually a reference resistors. Reference resistor. Then it goes to a transistor. It can be ground or minus VCC, doesn't matter, at the lower voltage level. It can sit at the lower voltage level. The collector is connected to the base. So essentially, this transistor has a VCD of 0 volt. Transistor, when collector to base voltage is 0, is still active. The reason is VCE is equal to VBE. Here, VCE is equal to VBE. That means not saturated. Not saturated. So IC will be equal to beta times IB. Perfectly well, transistor is active, and it's going to generate a current. So let me just put this here. You don't draw it because you have it in the handout. So this will be IB1, base current of 1, IC1, there is a current coming through that resistor. Usually it's called Iref. And that current is combination of IC1, here, IC1 plus IB1 plus IB2. IB2 will be the current going to the second transistor, IB2. So here is the format of the second. So that's a Q1, this is a Q2. And going up to provide provide current for the rest of the circuit. Okay. Here, of course, VCB number 2 is also greater or equal to 0. How far it can provide constant current, provided that the collector of that one with respect to the base is not lower. VCB of the 2 is positive. So this is B2, C2, E2. All right. So let's see what will happen now. You've got a current here. It's called IC2. IC2. So we need to put the equations into order. You know, KCL, that's all to it. So by KCL, IREF is equal to IC1 plus IB1 plus IB2. That's equation 1. But we notice that VBE of 1 is equal to VBE of 2. VBE of 1 here. VBE 1 is the same as VBE 2. Why? Because bases are the same node, emitters are the same node, then same potential. Whatever voltage is there is here, identically. Therefore, IC of 1 is equal to IC of 2. Equation 2. Why? If the base voltages are the same, collector currents are the same, well, recall that equation, classic equation. IC is equal to IS, e to the power VBE over VT. IS is the reverse saturation current, which is also temperature dependent, pretty strongly temperature dependent. VT is temperature dependent. So, but both are the same. IS for this guy is the same as IS for the other one. The reason is IS depends on mobility, concentration of doping, everything, because it is localized on the same chip, same vicinity, IS is identical to both. VT, identical to both, because they share the same temperature. Same temp, same IS. So right here, same temperature, and IS. The two are identical. So we get that equation number 2. So IB1, therefore, is going to be equal to IB2. IB of 2. Because, again, IB depends on the VBE in a transistor. Since VBEs are the same, the base currents will be the same. IB1 is equal to IB2. And therefore, at IB2 will be equal to IC2 divided by beta. This is equation 3. Equation 3. So both transistors have the same voltage, therefore their base currents will be identical to each other, equal. And base current will be collector current of the second one divided by beta. And also IB1, the base current of transistor number 1 will be IC1 divided by beta, which is identical to IC2 over beta. Why? Because ICs are the same. Here. ICs are the same. And IBs are the same. Now, we will substitute into that reference equation. For reference equation being IC1 plus the sum of these two currents, we are going to substitute the values for IB1, IC1, and IB2. So this will be the result. I reference in the resistor will be IC2 plus IC2 over beta plus IC2 over beta. Duplicate. These are two IBs that were equal. Now, here is the final relationship between the two. If you calculate IC2 in terms of IREF, it will be equal to beta over 2 plus beta multiplied by IREF. There it is. Provided both transistors are in active region. And the circuit should always keep both transistors in active. This one is, it can never be otherwise. because a collector can't go below the base, it's jumped to each other, so it's permanently active. This guy, however, has a chance. If collector voltage for some reason goes too low, hitting the ground, well, it will go into saturation, your current source will fail. It will fail. But it can go pretty low. The voltage in here can sink all the way to the proximity of this rail, which is a ground or negative VCC. So this current source is powerful because it has a large dynamic voltage range. If you design them with a plus 15 and a minus 15, practically the voltage in here can go all the way down to near minus 15. And still, the current source, mirror generator, will function as a mirror generator. It will do its designated function. It has a large dynamic range. For example, in here, look, in here you won't have that dynamic range. Here's a battery, 3 volt. Here's a transistor. Here's a resistor, 2.3 kilo ohm. All right. Here's a current. Indeed, this is a constant current, 1 milliamp. It's 3 volt. This is 2.3 volt. VE is 2.3 volt. RE is 2.3 K. Gives you 1 milliamp here. Roughly 1 milliamp over there. This is a current source, perfect current source. But check one limitation on that. How low that voltage can go. How low it can go before saturation. Your collector voltage in here can't go lower than 3 volt. That's VC has to be. Any question on that? Because if collector voltage here goes under the 3 volt, then VCB will become positive. Will become negative. Remember what was the rule? If this is 0.7, collector voltage can't be less than 0.7 with respect to emitter. So it restricts the voltage at the collector to minimum it can take is 3. Has to be equal or greater than 3 to stay active. To stay active. The reason that I brought this up about the what is the range it can be active, because there is a homework number 6 which has different current sources, and it is asking you for what range of input voltage, differential voltage range, the circuit will function. So you've got to watch that your current sources function. This current source will function if the rest of the circuit up there causes the voltage to go down. No less than 3, that's my limit. If this was minus 15, this would be minus 12, no less than minus 12, if it was minus 15. Or else it will fail. Yes?
This is because VCE has to be bigger than VBE, right?
Yeah, VCE has to be equal or greater than VB. That's the whole story. Then automatically it makes VCB positive. So if VCE, look, if VCE is greater than VBE, conclusion is VCB is greater or equal to 0. It's the obvious thing. If VCE is greater than VBE, collector voltage higher than if this is base, that's the emitter. If it is higher than that, then automatically VCB, that to this point, will be positive. Must be equal to 0, that's the minimum, or positive, to stay active. So actually, that is a current source. It's a current source that provides the rest of the design. Then you put an RC in here, you call that an RC in here, and you got this from a voltage divider or 1 or 2, etc. and you created, you know, an active circuit, you bypass that, and eventually the best you could get for RC was whatever you put in there to keep the circuit, this condition satisfied. But it's going to change in here. We've got advantage of that current source, which I will tell you, it is way superior over what we have over here. Actually, this one, as a current source, is not a bad current source. It's close to the ideal. Again, in a homework example, it shows why. We will get there in a minute. So let's see what happened right here. It generates that, it tells you that IC2 is kind of copying Iref. This ratio, if beta is high enough, the ratio will be nearly one, okay? So that means IC2 is equal to Iref. That means if you design a current path through this resistor and you inject the current there that you can predict well, then you can determine the current in the second transistor. So how can we establish a definite amount of current in the R reference? It's not hard. Here, put the voltage there, 12 volt. This is 0. That voltage is about 0.7, isn't that right? Okay. So the voltage drop on this one is 11.3 volt. So you want to generate 1 milliamp in there? Put 10 kilo ohm resistor in. 10 kilo. 11.3 divided by 10K, it will be 1.1 milliamp. There. You will get 1.1 milliamp over here. Almost 1.1 milliamp. It depends on the beta. How good is the beta? You will be surprised in NPN transistors, discrete ones, betas go to 100, 150 easily. But when it comes to the chips, ICs, betas are not that smart. Maybe betas will be 40, 50, 60, something like that. They're not that high. I think it's a technical thing in the design, you know, they can't make it too high. Because in a chip, if they make it too high, conductivity too high, there will be interference between the components. They will start crosstalking. So generally, betas over there is not that great. Okay, so this is going to be a possible, a viable current source over here that it can furnish a current in that path to whatever you want to bias. For example, is this going to bias a CE amplifier? I could have done that. I could take this to -12, grounded that. Check here. See if you understand it. This is 0, that's 12. If I change that to ground, 0, and change this one to -12, will there be a difference in the collector current here? No, because the reason is, check the voltage drop on the ref. It's 0 in here, this is -12, so this is -11.3. -11.3 is the same as -11.3 in here, reference to the 0 volt ground, makes 11.3 volt drop on the RF. So if I make it 10K, still I will get about 1 milli in this branch. That will mirror that 1 milli in that branch. But of course, with one exception, then the limiting voltage in here, which used to be no lower than 0.7 of a volt, it can go to no lower than -11.3 volts. So VC has to be greater than that, which is great. You know, that has a large active or dynamic range. It's a current source that has a large dynamic range. Okay. So this is the example by itself. If you want to know what is the values, like typical examples, tie this to a a supply, a ground, for example, calculate what's the current in here. Doesn't matter it's ground or something else. The current will be the same because it's a duplicate. It's independent of the VCE. And also, a voltage in there like 0 and the voltage in here like minus 12 volt, it makes this VCE well positive. So it's way greater than 0.7 of a volt. So that is functioning as an active transistor. So story is said about that. Looks great. Now, what is the dynamic resistance of the current source you created in here? I want you to understand that. What's the dynamic resistance? Okay, suppose it's at minus 12. It's a constant after all. In terms of AC model, it's a constant, minus 12. So how are we going to determine the dynamic impedance in here? For example, if I put a small signal V test, small signal, how much I test will flow into that circuit? Number one, if this transistor was ideal, in other words, VA was infinity, the change in the current would be 0, obviously. If something is fixed, it doesn't change. There is no signal IT. So whatever voltage you put in there, if the current doesn't change, there is no change in IT, voltage divided by 0, infinity. That will be infinite impedance. You know what it is referring to? When you look at the collector side to a transistor, RC, remember that internal resistance we always dismissed? RC will be infinity if VA is infinity. So you would have an ideal current source, and a current source delivering fixed current with infinite resistance, with infinite RC, but that never happens. So how much we can get? You have a VA, say 200 volt, 150 volts, say. You have a VA, you designed a 1 milliamp current source. What is the dynamic resistance? Okay? Let us erase that board. All right, so we go to this handout. Remember where I'm injecting between, say, supply and collector, let's say. Just doesn't matter. You take that 12 or not. When you do the model, small signal model, it ends up to be the same thing. So remember, these are constants. Constant, and that's a constant. Constant, it's a ground. And this is the source that you're injecting. So start drawing the small signal equivalent circuit. Start with the last one, our ref. Our ref. That end is ground. Then we get to the collector of this transistor. C of the 1. Post this resistor here, or O. Its emitter as grounded, emitter of 1 grounded. Then you have a constant current source here. That is called, that is generating a current in here, GM times VPE1. and then you have R pi, which is identical to the other one because collector currents are identical. And you have a base of 1, R pi. And this thing is VBE of 1. This is E1. Now, this was transistor Q1, transistor Q1. Next thing is the second stage. You have R pi, you have positive, negative VBE2, you have E2 grounded, then you have the current source, GM times VBE2, and then you have RO, collector to 2 emitter resistance. Here, RO is collector to emitter internal resistance. They're both equal because they both have the same collector current. ICs are the same. Okay, so that is the B, of course, B2, which is essentially as B1. Bases are connected. And this jumper is that line. And that is C2. And here is your test voltage you're putting in. This is the generator. We are sending a test voltage. End of the test voltage is either ground or positive supply. It doesn't matter which one you, because both are considered ground, fixed. V test, here is your I test. Okay, so V test over I test is the collector dynamic resistance, which is equal to current source internal resistance. Internal resistance. What is that? What was the process for determining the that test and I test business? You look at the left side. Look at this side. If I put a voltage in here, will that voltage excite a current in this path? There's no way. Do you see that? Because that voltage works across this combination here. It will not affect anything over there. It's like isolated circuit. That's the method to do. VT, and then you look at the propagation, how that current is going to influence this current source. I don't see any way of doing it. Because if this current is applied to this side, it's not going to change that voltage at all. You know, transistors work from input to the output. They don't work backward, right? Input controls the output. Output doesn't control the input. So it appears that if you put a voltage in here, there will be no change whatsoever in this part of the circuit. So VBE2, like VBE1, will be all 0. If they are 0, this will be out. Now you tell me what is the ratio of VT to IT. Isn't that RO? Yeah, it's the RO. So here you are. VT over IT is going to be RO. What is RO? We can figure it out. It is VCE plus the early voltage VA divided by IC2, VCE2. There we go. So this is the equation that will tell you what is that dynamic resistance. You've got to see what is your bias voltage, what is your early voltage for your transistor, and what is your choice of the current. Now, there is one thing that you will notice in here. Objective is to get a high RO, like large dynamic resistance, because that will be closer to the ideal current source. Isn't that right? When the internal resistance of the current source is high, the current source is closer to the ideal. That's obvious. And that explains why in practical transistors we have IC biasings of the order of about 0.2 milliamp, maybe even 50 microamp. That's news, that's a new thing to you. Because remember, we always took IC collector current bias 1 milliamp, 2 milliamp, 4 milliamp, right? Well, that's for the CE amplifier design. It's not for the differential amplifier design. But if you want to get a large dynamic resistance, the choice wouldn't be like 1 milliamp. The choice is probably 0.2 of a milliamp, 0.2 to maybe half a milliamp, 500 microamp, that's it. So why we are doing that? Why we are lowering IC? Because you increase RO. When you increase RO, you get more idealistic current source. More ideal current source. So we're understanding the philosophy why you want to get that small current here, 0.2 milliamp. Well, because that will give you a larger dynamic resistance. It's better, larger dynamic resistance. And that's what we're looking for, a current source with a large dynamic resistance. Okay, so this is the model for current mirror generator, which the diagram is drawn over there. Now, do you want me to solve a problem on this? Before solving a problem? I'll give you VA and everything, go figure out the values. Let's say, if you take value for VA, identical VAs for both transistors, all you need to do is to calculate the IC of each one, especially the IC of the second one, because this one doesn't matter, really. We don't care about that part. It does nothing. This part did nothing, basically, to determine the RO, output impedance. And then you simply see how much is IREF here, the current in here, which can be calculated very comfortably from voltage across that resistor divided by the size of the resistance. That's it. 0.7 here, whatever the supply is, figure it out. You can calculate IREF, and that IREF is almost equal to the IC of number 2 with a count with beta. Just a little bit less, unnoticeably less. It's beta over 2 plus beta. So if you set 1 milliamp in here, there you're going to get, say beta is 50. 50 over 52 times of the 1 milliamp. Tad short of 1 milliamp. And once you have the 1 milliamp over there, you want to know what is the dynamic resistance, here you are. You go to this equation, IC is, say 1 milliamp, you know what is VA, stick it in, VCE2. VCE2 is the collector to emitter voltage. That means it depends where you are connecting that collector. But notice one important thing. This equation is exact, but it has one problem. You need to know what is VCE2, right? Another smart equation is RO approximately equal to VA over ICT. What is good thing about that equation? You don't need to know VCE2 to figure it out. All you need to know is current, size of the early voltage. This is very kind of a valid statement if VCE2 happens to be much smaller than VA, and usually that is the case. In semiconductors, this goes to about 10 to 15. VA goes to 100 to 200. So that is hardly 10% of that number. So this will give you a good estimation of what is RO, dynamic resistance. This one, estimating RO. Okay, so there's no need to put numbers over there to calculate. Otherwise, that's what it is. You just try it by yourself and with these facts. Okay, improvement now. Generally, if you put a resistance in the emitter path and you make the transistor act like a current source, you're going to get a dynamic resistance at the collector, which is going to be way higher than the RO of the transistor. You know what? I'm going to show you with this example, which is simplified version. Let us say, instead of BJT, let us select FET. Why? FETs don't have arc line, and they have a very simple model. An FET with its RO. And let us prove what is the dynamic resistance. Actually, this was one of the midterm exam questions. Final exam questions, which we were supposed to determine, draw a model and calculate it. So here is how I will put that question to you. To see the influence of that RE. Here. Let's say this is 5 volt. This is RS. That's the drain. Here's the source. Here's the G. We know IG is 0. IG is equal to 0. And assume VDS is greater than VGS minus VTN. So i.e. Transistor is in saturation region. Transistor is well into saturation region, especially if drain to source voltage is much greater than the gate to source voltage, whatever it is, minus the threshold voltage. So question is this. Say VCC. V test, I test, ID test. No, don't call it ID. Let's call it IT because it's a test anyway. That IT is going to be the ID. ID is given. How do we determine the drain current, the DC drain current? It's very easy actually. You have a G, voltage at the G, This is the VGS. There is an ID going through the RS, through that resistor. So you have an input load line here, V of the G minus VGS. And then ID, big ID, RS, minus RD, IS, equal to 0. And then you, this is called input load line. And here is the characteristics. ID against the VGS. This characteristic is only correct for saturation region. All right, that is the ID equal to Kn over 2 VGS minus VTN squared, and here is your load line. And this is your quiescent ID. And this is your quiescent VGS. Q. Okay. Which means the current that is established in your transistor. You know VGS, you know ID. Okay, so from here, once you find your ID and the VGS, and from the VDS that you have, you may have a VDS as well, in terms of that ID, because you may have something else up there, or this might be tied to a fixed voltage. You can figure out the VDS. From there, you can determine what is RO. RO is equal to, in FET, FET drain to source AC resistance. It is equal to, so let me remember what is that. I've got VDS 1 over lambda ID. Okay, this is equal to 1 plus lambda VDS divided by lambda times ID, where lambda is channel length modulation index. Channel length modulation index. The value of that lambda is between 0.01 to maybe 0.001 volt to the minus 1. So it is a very, very small, very small quantity. It's a parameter that you need to model. Ahead of the time, we should know that. So, knowing how much is ID, that has established from here, either from calculation or by the load line method, knowing how much we have established there, and knowing the situation in the circuit, what that drain voltage is sitting at, what level it is connected to, we should be able to calculate the RO. Okay? So RO can be determined anyway. So RO can be determined. Can be from circuit parameters. Okay. Now that we have determined, let's see what is the dynamic resistance. So check what we are doing here. Is this what? Is this a common source amplifier, common drain amplifier, or like a common gate amplifier? I say it's more like a common gate amplifier. What do you think? Because this is not bypassed. Not one. S is not common. Drain is not bypassed because we're going to inject the signal there. Gate, yes, it's not changing. So it is like common gate amplifier, a common gate amplifier that we are feeding from the drain side, an unusual place. You know what I mean? Instead of feeding from gate, getting out of the drain, or feeding through the source, getting out of the drain, you're feeding right from the drain, and we want to see how the current will change. That will determine the dynamic resistance. So what is the model? Can we construct the model for that transistor? Say you calculate GM here. Say you found GM from radical to Kn ID quiescent, approximately. We figured out GM. Now we are going to construct the AC model. Construct AC model. Here is your AC model. G, that's the gate. Straight to the ground, because this battery is a short circuit. Even if it wasn't a short circuit, it should be a ground, if there was a resistor divider, because there is no current going there to cause the voltage to change. So that voltage is permanent. Then, this is your source. You have a resistor there, RS. You have it because you need to bias it. Look, you need to get a load line to create a drain current. You must have it. Then, here, you have a current source. The current source is GM times VGS. What is VGS? This is VGS. Gate to source voltage. Then here is your drain. Then you have a resistance in here, RO, between drain and the source. Here is where you are driving that circuit. You took a test voltage and you're interested to see how much test current will flow in. If you could calculate VT over IT ratio, then that is going to be your dynamic drain resistance, the dynamic resistance of this current source, IDQ. So this IDQ is going to appear as a constant current or dynamic. This will be the IDQ. IDQ. So it will generate a quiescent current with internal dynamic. But you have to answer this question as what will be the value of RS. So how do we go about it? How do we solve that problem? Can we solve that problem? It's dependent source problem, see? That's a dependent source. It's a current source. It mimics whatever VGS is. So if this is IT, if that current is IT, gentlemen, this current is going to be also equal to IT, isn't that right? So this voltage is going to be plus and the minus RSIT. RSIT, that voltage. This voltage is VGS. Notice that your VGS is equal to minus RS times IT. minus RS times IT, okay? This is an important. Therefore, the current that is generated in here is going to be, this current is going to be minus RS times IT multiplied by GM. By GM. This is the current that is generated in this branch. Okay? Now you can calculate what is the voltage drop on that one. Because this voltage is known in terms of IT in that resistor. This voltage is known, it's the VT. Difference of the two will be the voltage drop on that resistor. Then you can say IT plus current in that resistor plus the current in that branch is equal. And eventually, this is what you're going to see. Show that, and you do it on both. Show that VT over IT R dynamic resistance is equal to 1 plus GM RS multiplied by RO. There you go. So the dynamic resistance you will see in here, gentlemen, here, is not going to be that resistor because of this RS. It's going to be this much. You've got GM, which is a multiplier with the RS. It looks like gain. You see that GMR? 10, 30, 40, 50. You get 50 times of RO at that point. So by planting a resistor in the source side or emitter side of the transistors, you can get a dynamic resistance not just equal to the collector to emitter, but gain times that, like GM, whatever RE is, which could be minimum 50 times to 100 or 200 times. So already RO is large, it's like 100K. But now we can get 200 times 100K, 20 megaohm, which is important. So the next current source, I will do it for you, is going to rely on that property. It has a different format for the sake of improving the dynamic resistance. So this is just a showing that it improves. Having that configuration, it improves. Okay. Tomorrow is going to be an exciting day. If you haven't voted, please go vote. Make up your mind. Understand what you're voting for, right? Then